Next in the exciting installment. Box on ground. Obviously, as we go, we're making it slightly more complicated. We're eventually working our way up to a test level problem. So first, draw the problem. Again, drawing the ground with the hash marks here to indicate that it is fixed. Now I have two boxes, so I'm just going to label them box 1 and box 2. Oftentimes I don't give them labeled like that. I will tell you the mass, in which case I would just use the mass as the symbol. First step, separate the drawings. Give myself plenty of room here, because I need to draw arrows without overlapping. So let's start out with what we can get rid of. Now the intent of the drawing is that everything is level here. So there is no friction because there's no desired motion. We definitely have contact, but no desired motion. There are no ropes, chains, or anything like that. I have no force that I've introduced into it. There is contact though, and there is a gravitational force because I've got a large object and two smaller objects, specifically I have weight. So let me pull, so there's obviously weight pulling down on this box here, and weight and the other one up here. Because this force here, this weight, is between the box and the ground. Now I have a second box here, and I'm going to introduce a mistake that's easily corrected. The mistake was not the bad drawing of the box. I'm going to introduce a mistake that we'll then talk about, and the reason why I'm doing box on ground, one of the reasons. So there's also a weight coming down here, and a weight coming up there. So this is another rookie mistake, is to leave it like that. The problem is the weight of the two boxes the same? It's the same magnitude. They're obviously both down, so I guess same vector too. We can't guarantee that. There's nothing in this problem that says that the weight of these two objects is the same. So we need to somehow differentiate these two weights here. And we do that with subscripts. So I like the subscript to have some meaning to the actual problem. And so I'm going to put a little 1 here for the weight of box 1. And so one of these is a 1 here. And then a 2 there and a 2 there. So when you have multiple pairs of the same type force, you need subscripts. So rookie mistake number, I guess, 3 would be to not do subscripts. Another rookie mistake is assuming that weight is between objects that have contact. Too many times I see people put a weight between box 1 and box 2. Now, to complicate it, there is a gravitational force between box 1 and box 2, but that force is so incredibly small, unless these are planet-sized boxes, that force is so incredibly small, we can ignore it. It has no impact unless you're doing the really high-intensity, multi-million-dollar physics experiments on gravitation. But even when I was doing my graduate work, I didn't care about that stuff because that force is so incredibly tiny. So gravitational force, done. Normal force. Normal force is between objects that touch each other. Obviously, box 2 and the ground touch each other, so I have a normal force acting up and a normal force acting down on the ground. Because I'm going to have another pair of normal forces, let me put the subscript in here, putting y2, because a good yg also works, or y, as long as the subscripts are different. Up here, there's contact between box 1 and box 2, so there's definitely a normal force here also. So I have this normal force acting up on 1 and a normal force acting down on box 2. It is y1 here because it's the force I'm associated with box 1 as well. Now technically, the two W2 arrows need to be the same length. The two W1 arrows need to be the same length. The Y1s need to be the same length. The Y2s need to be the same length. Y1 and Y2 the same length? No, they're not going to be in this situation. But that's why we're using the labels here. I do want to point out 2 things here. One, you often see something known as a free body diagram. And in a free body diagram, you reduce the object to a single point. And so you have a point here, and this would be box 1. And you have an arrow up of Y1 and an arrow down of W1. Then you got another arrow, another dot here, box 2. with y2 acting up, and then two forces acting down, y1 and w2. And then you have the ground. And I have two forces acting up, w1, w2, and y2 acting down. I'm not as big a fan of the free body diagram because probably the engineering training that I have, where the force is applied matters at some point, especially for those who are future civil engineers. It becomes incredibly crucial. And so by drawing the sort of two-dimensional figure instead of the zero-dimensional figure, you can start to reflect where the force is actually applied. And especially when we get into rotational motion, where the force is applied becomes critical there. So I really prefer this one. It makes the transition to rotational motion a little bit easier, in my opinion. But some people prefer this. And so if you're looking at other sources, you often see it this way. Now, this actually does have a practical application. So instead of box on ground, we're going to do person on scale on floor. So I have my floor, I have a scale, and person. Now the floor is fixed here. I'm assuming that the floor is somehow attached to the earth, so this is still representing the planet, even though it might be the floor in your house. If I treat the house as part of the planet, it still works. Now the force diagram is going to look the same. I'm going to change my subscripts a little bit to reflect the problem. So there are the three objects. I have a normal force acting up on the person. I'm going to call it y sub p. And then there's a y sub p here. There is normal force between the scale and the ground, so I have y sub s and y sub s. There's weight involved, so I have weight of the person and weight of the person, and then weight of the scale, weight of the scale. Take a moment just to convince yourself that it's the same other than subscripts. Pause it if you need to. And so the question is, what does the scale actually measure? Most people immediately think scales measure weight, and that's sort of what is taught. But technically, it really doesn't measure weight at all, because the weight of the person is not acting on the scale. The only weight acting on the scale is the weight of the scale itself. Let me clean up that subscript there. The weight of the person is acting on the planet. The only force that the person exerts on the scale is this right here. That normal force from the person is what the scale measures. So if you're on an analog scale and bouncing up and down, you're going to see that needle move a lot, because not that your weight has changed, it's just the normal force is changing. Now, so why do we claim it measures weight? Well, if the person is in equilibrium, so if in equilibrium, and flashback, there are actually three conditions for equilibrium. If one of them true, the other two are true also. So one of the conditions is that acceleration is 0. And if acceleration is 0, it means the change in velocity is 0. Not that the velocity is 0, change in velocity is 0. And the total force is 0. Those are all zeros, not O's. So if the person is in equilibrium, the total force acting on him must be 0. In other words, the force up equals the force down. So if he's in equilibrium, y sub p is equal to w sub p. So the normal force and the weight are the same, have the same value, I should say. And so that is why, since the normal force was applied to the scale, if he's in equilibrium, the normal force is what's being measured, and that should be equal in magnitude to the weight.